Hello.
Hi.
Hi, Nancy.
Hey.
Okay, so what's your favorite 90s movie?
I must say, it's not like, well, I don't know if it's a typical 90s movie, but I watched it a lot in the 90s, and it was made in the 90s.
Oh my God, it's an answer.
That is the definition of a 90s movie.
Yeah. Lauren, like, I have to say something.
Dazed and Confused.
Oh, that's a good one.
That's a good one. Why is that not a typical 90s movie?
I don't know.
It doesn't have to be about the 90s.
No, I know. I guess not. I guess because I'm saying that because it takes place in the 70s, which is a dumb reason.
That's not a good
totally
reason.
dumb reason.
Have you, so like one of the quintessential 90s movies I think of is Twister.
I've never seen Twister.
You've never seen Twister?
I never even
How
really
have you
heard of it.
never seen Twister?
I've never really heard of this movie.
It's like
I don't
a
know.
classic 90s
How did
action
that
movie.
escape me?
I don't
don't
know.
know.
Like,
I don't really like action movies.
Is this your East Coast bias?
It's a twister. Is that what people say? Is that what they say in the movie?
No. Nope.
Oh my gosh, we are going to get so many comments on this. Welcome to the American Geophysical Union's podcast about the scientists and the methods behind the science. These are the stories you won't read in the manuscript or hear in a lecture. I'm Shane Hanlon.
And I'm Nancy Bompey.
And it's the third pod from the sun.
Did you know that Twister was actually based on a real research project?
No, because I never saw the movie.
I have seen the movie.
Does that make you want to see it now?
Perhaps.
Yeah, see, I didn't know that. I want to watch it again.
Yeah, I just found out. I met a meteorologist, Jana Houser, and she goes out and chases tornadoes as part of her job, just like Helen Hunt.
My name is Dr. Jana Houser, and I am an assistant professor at Ohio University. When it comes to research, my general focus is looking at radar observations of tornadoes and the storms that produce those tornadoes.
Tell me a little bit about how you got into studying tornadoes. Was this always kind of a goal of yours in meteorology, or did it kind of just happen?
I became interested in tornadoes specifically at a very early age. I wasn't watching cartoons. I was watching the Weather Channel, and I asked my dad to get me videos of tornadoes and hurricanes. You know, now this is getting into like maybe the early 90s where we have, you know, Jim Cantori who still has hair and, you know, back in the day of all that. And once I really kind of got into that, I just totally fell in love, particularly with tornadoes. And ever since then, it's kind of been a one-track course to get me to where I am.
Power flash. Another power flash. Power flashes. All right.
Awesome. When was the first time you went out to chase a storm?
The first time I went out to chase a storm was in 2004. I was a junior at Penn State, and the very first day I was chasing was still probably like one of my top 5 chases, and now I've been chasing for over 15 years. The very first day we were out, we were in south central Kansas, and we were driving, and sort of out of the blue, like literally it didn't seem like there should be a tornado. We heard over the radio, oh, hey, look, there's a tornado over there. And looked out the window, and there's this tornado that's just kind of like in the middle of the field, and there was even a rainbow nearby. I mean, it was very like kind of surreal and like almost other earthly, because it kind of like you have this sort of contradiction between this tornado, which, you know, hypothetically, you know, is incurring damage somewhere, and but then you have this like placid rainbow right by that kind of like creates this sense of just like all is well, and look at this pretty tornado, and you know, so it was kind of a moment of like, oh wow, you know, that's interesting. But the moment that was kind of more energizing to me than that very first tornado was the next storm that we collected data on. And I can remember very clearly, I can picture the deployment spot in my head. I know even to this day when I pass that spot, I'm like, oh, that's the spot where I saw my, you know, first real, like, exciting sort of tornado. And I can remember I was driving the radar truck, and we were sitting collecting data, so I wasn't driving at the time. But we were operating with the second radar, and the other radar operator was saying, oh yeah, look, we've got another tornado on the ground. And we were looking, and for whatever reason, from our vantage point, we just couldn't see this tornado. And there was a small rise in the ground surface, not too far away from us, and it was just enough that it obscured the tornado from our vision. And we're like, where is this thing? Where is this thing? And we are seeing it now on our radar, and it's relatively close, and we're seeing it, and then all of a sudden, like visually, there it was, and it was close. I mean, I don't know really how close it was. We weren't in an unsafe position, but being like the first time that I was really out in the field, I was like, oh my gosh, tornado, like right there. And I didn't know whether to like be ecstatic or to cry. It was kind of this like weird confliction of emotion where I was just like thrilled to be really seeing a tornado relatively up close for the first time in my life, and at the same time being like slightly petrified with fear, not knowing what is exactly happening.
Beautiful multi-vortex, looks like an appreciable tornado just to our south. Looks like we're going to be north side. We might get some large hail.
Okay, great. Thank you. We'll be right
Look at the horizontal vortices feeding on the left side. Holy heck.
So we stayed at this location, and I was with my my mentor at the time. She was is still a faculty member at Penn State, and she's a very calm woman. And I remember her getting on the radio and saying, so this tornado's getting a little close. Do you think we should, consider moving south a little bit? And the radar operator was like, no, you'll be fine, you'll be fine. So we waited out for a little bit, and, it's getting closer and closer. And she gets on the radio again, a little bit more kind of emotion in her voice and saying, this is really close. I think we're going to move now. And they're like, no, you'll be fine. So she stops. She's like, we're moving. And just, executive decision made right then. So we're trying to, blast south away from this tornado. And I remember actually laughing. And I think I might have even called my mom, like, as I'm driving away from this tornado. So we're trying to drive away from this tornado into winds that are at least 40 miles per hour that are basically being sucked into the storm.
Oh my God.
And I had the pedal to the floor, and we were going 45 miles per hour. And that was the fastest I could get that truck to go. So
were you terrified? What were you feeling?
I was like, I don't think I was terrified. I do remember laughing very probably like maniacally. But it was those kind of like excitement and a little bit of fear and just total exhilaration of what I was seeing and just the craziness of that particular situation and scenario that I was in at that moment.
Did she say they were driving a radar truck?
So did they actually drive a radar truck in this movie you speak of,
God,
Twister?
Nancy.
God, Nancy, yes. There's a classic scene where the big red truck gets picked up and dropped in the middle of the road.
I'm not even gonna say spoiler warnings because everyone's seen this movie.
You can't spoil a movie that's been out for 20 years. So yes, they drive a radar truck, and it's basically like a Doppler radar system that meteorologists use to track storms and clouds and rain and weather. But it's small and it can fit on the back of a pickup truck, so they can drive around with it, take it wherever they need to go. It's kind of like a big satellite dish, essentially, with a big antenna.
It's not like Dorothy.
We're gonna get to that later, Shane.
Oh, I'm spoiling.
What's Dorothy? Is that part of the movie too?
Yes,
We'll get there.
We'll get there.
All right. Well, how do they know? So then, how do they know where the tornado is going to be or where to go? Or
Well, they don't.
It's very challenging to determine beforehand where the tornado is going to actually form or which storm is going to produce the tornado, especially when you don't even have storms to begin with. Mm-hmm. So we tend to go out in a general direction, and we're monitoring the conditions essentially nonstop. It's essentially 18 hours almost straight of constant data coming in, a constant reevaluation of what's happening. So as we get a better feel for the conditions as we're going throughout the day, then we start to hone in on potential more precise areas, like specific towns where we think we want to target based upon the temperature conditions and the wind conditions and what things are looking like above the ground. Mm-hmm. So depending on how far the drive is, we might need to take 4 hours to get there. We might be in a good position to begin with, in which case you just basically find a Walmart or a gas station and you essentially sit sometimes for hours at a time until the atmosphere actually makes storms. And then the trickiest part is when you have multiple storms that are forming, trying to figure out which one is going to produce the tornado. And there is no science specifically to that. Oftentimes it is just luck. But a lot of times there's a lot of external factors that come into play, like, did you get stuck behind the train that's going 5 miles per hour and you're sitting for 20 minutes behind this train, and then you're trying to blast towards where a storm is forming and you end up missing the tornado by 15 minutes and you think, man, if it just were not for that darn train, we would have been there, you know?
Oh, God.
And sometimes there's road network issues where you have a storm, but you just physically cannot get to it because the road network won't let you. And sometimes that can, mean that you miss the tornado as you're driving and you're, 25 miles away from the storm and it's producing a tornado and there's just not a road there to get to.
What was your most memorable chase? Do you think it was that one, or was there another one?
The most memorable chase, though, that I had was actually my last year of graduate school. This was 2013. And this was on the tornado that went through Reno, Oklahoma, and unfortunately killed 3 storm chasers. So,
oh, my God.
Yeah, so this was May 31st of 2013.
Good morning from the National Weather Service Norman Forecast Office. Here's a special early morning severe weather outlook to help you plan your day today. It's a complex forecast. This is not a slam dunk automatic easy forecast today. There's some elements that make it a little bit complicated. We do think we have the highest tornado potential that we've seen this week today. The storms we'll be most concerned about will be the area along the dry line there, and we will look for isolated supercell storms to develop, probably closer to that 4 to 6 p.m. time frame, but we'll be watching out by mid-afternoon, and those could be severe very, very quickly with very large destructive hail. We had over softball-size hail reported yesterday. We'll see that again today, and the tornado threat will be increasing as we get toward evening.
And I remember deploying on that storm before it produced a tornado, and it just was so mean looking. Like, I guess to somebody who's never really seen a tornado, you might not understand the difference that the sky is in certain conditions. So in some cases you might have a tornado that's kind of, like I was describing earlier, like almost delicate and kind of like just pretty and more aesthetic. And the sky looks different. And then you have these rare situations where you have these long-lived, violent, multiple-mile-wide tornadoes, and the storm is very different. And this was a situation on that particular day, and I can remember watching the clouds just swirling before the tornado happened, and they were so low and they were so black, and it was sort of this sense of almost like doom. It was very much like this storm could be really bad. So we set up our radar and we deployed and we were collecting data, and the tornado happened, and it was very much a pretty scary tornado, and it behaved a little bit unusually. It went to the southeast. Most of the time, tornadoes that are forming in the northern hemisphere move off to the northeast. So very commonly people try to escape south on a road to get out of the way of a tornado.
Mm-hmm. Getting big. Clear slot behind it, I think. Oh, it's now south of our. Oh boy.
So I was, again, driving the radar, and my colleague was operating the radar in the back, and I wasn't able to exactly see the display that he was seeing. So as this thing was getting closer, and it was very wide, we started talking about our undeployment strategies and trying to figure out, what our best route was. So I asked, we were at an intersection where there was a freeway that went east-west, and we were on a state highway that went north-south, or very close to a state highway that went north-south. So I asked the radar operator, I said, Jeff, do you think we should go south now? And he said, no, do not go south. You need to go east right now. And I'm really grateful for that, because had we gone south, there was a slew of people that were going south on this state highway, but that was the road that ended up the chasers that ended up dying were trying to do the exact same thing and go south on this road, and the tornado was so broad and there were so many, it wasn't a single funnel, it was a multiple vortex tornado, so there were smaller funnels that were kind of rotating around a larger central axis of rotation.
Oh, wow.
And they just happened to kind of be in the wrong place at the wrong time in one of these smaller scale vortices, which by the way are more intense than the single wider tornadoes. One of those smaller vortices just kind of sucked them up, and unfortunately that was that. And they were they were very, very highly esteemed chasers, and it was very just a catastrophic day. I can remember then after that, we didn't know any of this was going on at the time. So after we blasted off to the east, we had another deployment a little bit later on, and there was like leaves and debris just falling from the sky that had been, and this was around the time that the tornado was dissipating. So all of this debris had been lofted up and was basically falling out as the updraft supporting the tornado was weakening. And then later, so not much later, maybe half an hour later or so, we were trying to drive east to stay with the storm that was producing these tornadoes. There was basically, we were getting into the Oklahoma City metro area, and there was basically mass panic about this approaching storm that just produced this huge tornado, which, by the way, our radar estimated was more than 2.5 miles wide.
Oh my God.
So and with wind speeds over 300 miles per hour. So this was a beast.
That is the biggest tornado I've ever seen.
In fact, that now holds the record as being the widest tornado on record.
I've seen like video and things of like massive tornadoes like online and stuff, that I can't imagine but being part of that, like that has to be just like terrifying, and like the like how deadly it is. And I don't know, like the loss is so like hard to imagine.
Yeah, and it was just huge. It was miles wide, miles. I can't even imagine it.
That's insane.
Yeah.
So what did they learn from this? I guess from science. Did they learn? They obviously got some science out of this.
Yeah, it wasn't just, a tragedy. They actually learned a lot. And so there were tons and tons of storm chasers on this storm. They were there photographing it. They were there videotaping it. And Jana was there collecting her radar data. And so something interesting happened when she compared the visual observations to her radar data. She discovered something really kind of crazy about how tornadoes form.
So Anton Simon basically put together this project that was entirely self-imposed, and he collected video and still photography from as many chasers as would contribute to him, and he geolocated everybody through GPS, as well as identifying landmarks in their still and video photography, and then geosynchronized with using lightning flashes to determine the exact precise time of everybody's videos. So
wow.
The videos are all within roughly 1 millisecond of each other. They're all GPS coordinated and geo-referenced within, I think, around something like 10 feet or something like that. Our radar collected basically an unprecedented data set on that day, where we were collecting data at very, very low levels to the ground. We just happened to be at a good location with a really good view off to where the tornado was located. There was nothing inhibiting our viewing angle, meaning there were no trees or phone poles or barns or anything like that inhibited the propagation of the radar beam. And we were also slightly on a rise, so we could scan at an elevation that was basically parallel to the ground. Most of the time you can't do that because the radar beam is not truly it's not like a laser, it's more like an ice cream cone. Mm-hmm. So if you try to scan parallel to the ground, a portion of your radar beam actually intersects the ground and it contaminates the data. So you don't get reliable data at that lowest elevation angle. So from the radar data sense, this particular case study was something that was really pretty unprecedented. Then we coupled that with visual observations from Anton's group to essentially put together a story about how the rotation associated with the tornado formed. So the initial motivation behind this project was that I was reading Anton's paper, and he had a picture of a tornado that was about 2 minutes earlier than what we in my research group published as tornado formation time based on the radar data. So I was a little bit I was a little confused about that at first. I was like, well, this is very clear that there's a tornado at this time. I mean, there's a funnel cloud. There's no denying from the visual aspect that there is a tornado on the ground. So why didn't we define it earlier in our radar data?
So they saw it before your radar picked it up.
That's right. Yes. So it turns out that there's defining what a tornado is, when you really get down to the nitty-gritties, is very complicated. So we all sort of have this idea of, okay, well, you have this funnel cloud and it's in contact with the ground and you have strong winds, etc. And yes, that is what a tornado is. But then you get into these nuances like, if you have really strong winds at the ground but no funnel cloud, when is it a tornado? What is required in the radar data to confirm that an area of rotation is a tornado. So getting back to this sort of discrepancy in the time, we had defined the formation time of the tornado as when we saw a signature of rotation associated with the tornado essentially throughout the vertical elevation domain that we had in our radar data. So essentially you have this vertically continuous circulation associated with the tornado. And that's pretty traditionally the way we define tornadoes from a radar perspective. But then obviously we have this visual confirmation of a tornado before that. So I went back through the data and I could not find evidence of this tornado. And I'm scratching my head and I'm like, what am I missing here? Well, what it turned out to be is that I was not looking at the data from the lowest elevation scan, that 0 degree elevation scan, because traditionally, as I described earlier, we throw it out because it's contaminated and we don't use it. However, this data set had higher quality data at that lowest elevation angle. And it so happened that the only evidence of strong tornadic scale rotation in that radar volume was at that lowest elevation angle at 0 degrees. So essentially what we found was there was a tornado confined to very shallow vertical heights in, again, below 300 meters. And this persisted for about a minute and a half, not quite 2 minutes, prior to the onset of the deeper, more continuous vortex.
What does all this tell you about tornadoes?
Let me back up a little bit here. There has been a traditional disagreement about the way tornadoes form. Back in the 1970s, there was a series of studies that came out that suggested tornadoes form from rotation that strengthens at mid-level. So we're talking several kilometers above the ground. It strengthens there and basically draws air in from below, bringing that air toward the center of rotation, causing the rotation to get stronger at progressively lower and lower elevations until it intersects the surface, at which time a tornado forms. So this is good from a forecasting perspective because if a forecaster sees this area of strong rotation aloft, they can say, oh, let's monitor this for potential tornado development. And the process is relatively long. It takes, maybe 10 minutes or so. And there was some evidence observationally to support that from the new era, quote unquote, new era of Doppler radars that were just coming around in the 1970s. So there's a second hypothesis that has been used to explain tornadoes predominantly not occurring with supercells, which are the parent storm mode associated with the most violent tornadoes. But when you have like a line of storms, for example, it has been described as this bottom-up process where you have rotation that's induced by strong horizontal changes in wind speed associated with a squall line, or basically a big forward surge of fast-moving air. And then that kind of spins up into a tornado. Getting back to your original question, what does this mean as far as seeing this really low-level tornado? What it means is that you are not going to really ever be finding strong evidence of a tornado descending. So we need to stop making that a priority in our forecasting strategies, and we need to reevaluate the way we are issuing warnings and the types of signals that we are using to make those warnings. And I'm a pretty fervent believer that one of the reasons why we have so many false alarms in this era is because people do look for that mid-level rotation, and they say, okay, we see the strong mid-level rotation, and take that to be kind of a trigger.
All right, so we've been alluding to Twister, this movie that Nancy has never seen, a lot. But there are some obvious parallels there, right?
Well, yeah. So Shane, remember the name of the instrument?
Oh, this is where Dorothy comes in.
This is where Dorothy comes in.
Like Wizard of Oz. I've seen that.
Okay, well, that's good at least. Very surprised. So actually, the Dorothy in Twister is based on a real project, and Jana told me all about it.
So the movie Twister is actually based on a real project that was it was an instrument called TOTO. Go figure. TOTO was an acronym for the Totable Tornado Observatory, and basically it was this big cylinder like a water tank that was brought out into the field to ideally place it in the line of an approaching tornado, and it was equipped with sensors, like pressure sensors, temperature, moisture sensors, etc. Now, it did not have like the lid that came off and all of these fun little like whirly birds going up into the storm, but the scientific basis was again based on a real field campaign. Now, we joke in the field about it, these little sensors that just get sucked up into the tornado. And I'm not an engineer, so I don't know how, feasible that truly is. The challenge will be to deploy that safely in a location where it can actually be ingested into the tornado.
Right. Yeah. So what happened with the Toto project?
The Toto project ended up basically failing because they could not deploy the instrument where the tornadoes were. I mean, big surprise, right? You have this sort of perspective, especially when you go and see YouTube videos now, and there's just like video everywhere that like it's pretty easy to make an intercept with a tornado. The reality is it's really not that easy. You really have to work hard. And again, as I was mentioning before, really early in our discussion with the logistics of road networks and things like that, for one, you gotta anticipate where the tornado is going to be maybe 5 minutes down the road, which may or may not be, true. And two, tornadoes are actually really, in general, pretty narrow. The average tornado is on the order of about 200 meters or so wide. So it's not that wide.
That seems pretty big to me.
Well, if you think about miles and miles and miles of road that are stretching, and you have to, you have a tornado that's approaching, and you have to put this instrument in the line of this, 200 meter wide tornado as it's moving across the fields. It's a pretty challenging feat to accomplish. So Toto was ultimately a little bit of a failure, unfortunately. But I should extrapolate and say that the idea then has been sort of reassessed and redesigned, and there have been teams to produce these little triangular pods, and they basically aerodynamically get pressed down to the surface as a tornado is moving by, and there has been some success deploying those pods and getting video of the tornado as it moves over and recording pressure and moisture and temperature and so forth. And unfortunately, the video is not nearly as cool as you would hope it would be. Like, I love the idea in Twister where you have this like little tiny circulation like in the very middle, and then there's this clear air, and then there's like the big tornado outside, And there's actually some evidence to suggest from a radar perspective that something like that might actually sort of exist. So what we would love to see in a video would be like a confirmation of that. But unfortunately, these little turtles being so low to the ground basically just become totally caked with mud. Yeah. And you don't end up with, you almost like need a little windshield washer or windshield wiper there that's kind of like clearing off the camera lens or something like that.
Yeah. How many times in your career when you went out chasing did you just was there just nothing?
more times than I went out and saw something. I would say as far as like, successful tornado days, maybe like 10% of my tornado chases have been what I would consider, successful.
Wow.
So it's a lot of driving. But that 10%, maybe 15%, just like blow the other 85% out of the water and just make you sucked into this whole, this whole idea of seeing a tornado and just living that experience.
So Nancy, are you going to go see Twister now?
I mean, maybe. Although I feel like, after this episode, I have a pretty good sense of, what occurs. But I have a feeling
there's
the
so
movie's
much
a
more
little
drama.
different.
It's a little different. Yeah.
It's so suspenseful. You have to see it.
Yeah. We'll have a watch party.
Yeah.
Ooh.
Yeah.
It'll be fun.
If anyone's in the DC area and wants to come to our Twister watch party, you're more than welcome to come. All right, folks. Well, that's all from Third Pod from the Sun.
Thanks so much to Lauren for bringing us this story and to Jana for sharing her work with us.
The podcast is also produced with help from Josh Spicer, Olivia Ambrosio, Katie Brundle, and Liza Lester. And thanks to Adele Coleman for producing this episode.
We would love to hear your thoughts on our podcast. Please rate and review us. And of course, you can hear new episodes wherever you get your podcasts and always at thirdpodfromthesun.com.
Thanks all, and we'll see you next time.